first chapter in the first unit. So we'll move on to the second unit, which relates with the volumetric strain and the elastic constants. So you have seen what do you mean by volumetric strain. So volumetric strain can be defined as ratio of change in volume by original volume. Volumetric strain is ratio of change in volume by original value. We will derive some expressions for a rectangular bar as well as for a cylindrical bar subjected to a single direct load which is acting along the length. So first we will derive an expression for a rectangular bar subjected to single direct load. So I consider a rectangular bar having a length L, width B and depth D, subjected to axial force F. So let the variation along length, width and depth and represent in terms of coordinates x, y and z. Now under the application of the force, there will be an increase in the length, decrease in the width and decrease in the depth. So first we will define what is the volume of this rectangular block. So volume V equal to length into width into depth. So because of the application of the force, there will be change in the length, there will be change in the width, there will be change in the depth, as a result of which there will be change in the volume. So we can represent delta V as, there is a change in the length by keeping width and depth as constant, there is a change in the width by keeping length and depth as constant, and there will be change in the depth by keeping length and width as constant. So totally there will be change in length, width and depth. So I can write mathematically as change in the length by keeping width and depth as constant plus change in the width by taking length and depth as constant plus change in the depth by keeping length and width as constant. So delta V is delta L into Vd plus L into delta V into D plus LV into delta D. Now if you divide change in the volume by original volume, we will get the volumetric strain. It is delta L to V into D by L into V into D, L into delta V into D by L into V into D plus L into V into delta D by L into V into D. So these things will get cancelled. So left out is delta V by V equal to delta L by L plus delta V by V plus delta D by D. So delta V by V is nothing but volumetric strain. So delta L by L is nothing but longitudinal strain, that is the strain along X. Delta V by D is lateral strain, that is the strain along Y. Delta D by D is the lateral strain again, that is the change strain along Z. Now strain along X is nothing but the longitudinal strain is epsilon X is given by sigma by Young's modulus. Longitudinal strain which is also given by sigma by Young's modulus. So strain along Y, which is nothing but lateral strain, it is epsilon Y. I can write in terms of Poisson's ratio, where Poisson's ratio equal to lateral strain by longitudinal strain. So I can write this as mu into sigma by E. But since it is lateral, I will put negative sign, where negative sign indicates that the effect is opposite. That is, there is a change in length that is increasing, there is a change in width that is decreasing. to differentiate between increase and decrease, here I use positive sign and here I use negative sign. So lateral strain equal to Poisson's ratio into longitudinal strain epsilon x with a negative sign. Similarly, strain along Z, which is again lateral strain epsilon Z equal to again minus mu into sigma by. So volumetric strain equal to longitudinal strain sigma by E, lateral strain minus mu into sigma by E, again lateral strain along Z minus mu into sigma by E, or I can simplify it and write sigma by E into 1 minus 2U. So this is the expression for volumetric strain in terms of longitudinal strain as well as Poisson's ratio. So this is the expression for volumetric strain of a rectangular bar. Similarly, we will see what will be the variation in dimensions when we consider a cylindrical bar. Consider a cylindrical bar so this axis length L is the diameter D, subjected to a direct load, an axial force F. So, in the same fashion, volume of the cylindrical bar is pi d square by 4 into L. So, change in volume, there is a change in diameter by keeping length as constant, change in length by keeping diameter as constant. So, delta V equal to pi d square by 4 into delta L. That is, I have kept D as constant by varying the length. Now I will vary diameter by keeping L as constant. So differentiation of D square is 2D by 4. So pi by 4 into differentiation of 2D is, sorry, D square is 2D into delta D into L. I have varied delta L by keeping D as constant. I have varied diameter by keeping length as constant. Now delta V by V is nothing but pi d square by 4 into delta L by pi d square by 4 into L plus pi by 4 into 2D into delta D into L by pi by 4 into D square into L. So this will get cancelled. This pi by 4, pi by 4, and D will get cancelled. Length and length will get cancelled. So left out with delta V by V equal to delta L by L plus 2 into delta D by D. Or delta V by V equal to delta L by L plus delta D by D plus delta D by D. So the meaning is, if I consider this as x-axis, y-axis and z-axis, along x there is change in length, this is what you have shown here. Along width there is a change in the diameter, and along depth also there is a change in diameter, because if I consider the cylindrical cross section, which is cylinder, it is a circle, so along the width it is diameter, and along the depth also it is diameter. So along the width the change is delta D by D, along the depth also the change is delta D by D. So we can write this as epsilon V equal to epsilon x plus epsilon y plus epsilon z. So strain along x, it is longitudinal strain, epsilon x equal to sigma by E strain along y is epsilon y equal to minus mu into sigma by E. Strain along z, epsilon z equal to minus mu into sigma by E. So total strain, that is a volumetric strain, equal to epsilon x is sigma by E minus mu into sigma by E minus mu into sigma by E, or it is sigma by E into 1 minus 2 mu. So whatever may be the cross section, finally the expression for volumetric strain will be sigma by E into 1 minus 2 mu. Similarly, we can derive the same expression for a sphere, but the change is, instead of length, we will be having again diameter. So if I consider a sphere, the change is in the formula for volume and formula for volumetric strain. So volume is given by pi by 6 into d cube. So if we differentiate this volume and if we divide by the original volume, we will be getting delta d by d plus delta d by d plus delta d by d. It is along x, y and z. Only the variable is the diameter. There is no length for a sphere. So delta d by d plus delta d by d plus delta d by d. That is 3 into delta d by d. So difference between cylinder and a sphere is, instead of delta L by L, delta L by L is replaced by delta d by d. As a result, instead of 2 into delta d by d, we will be getting 3 into delta d by d. So that is the expression for volumetric strain of a sphere in terms of diameter. So now we will move on. Expression for volumetric strain. Expression for volumetric strain due to 3 mutually perpendicular stresses. Due to 3 mutually perpendicular stresses, which is also given by generalized Hooke's law, which is also called as generalized Hooke's law. So here, instead of a single force, single stress acting, I will consider 3 stresses which are acting mutually perpendicular to each other, sigma 1, sigma 2 and sigma 3. So for deriving that, I will consider a cube where this is the length, this is the width and this is the depth. So variation is represented by x, y and z. So along the first phase, the tensile stress sigma 1 is acting along x. Along y, there is a stress which is acting, that is sigma 2 tensile. And along z is again tensile stress, it is sigma 3. So sigma 1 is perpendicular to the cross section area, width into depth. Sigma 2 is perpendicular to the cross sectional area, length into depth. And sigma 3 is perpendicular to the cross sectional area, length into width. So all these three stresses are mutually perpendicular to each other. So you can observe here that sigma 1 is producing longitudinal strain along x. At the same time, it will be producing lateral strain along y and z. Sigma 2 will be producing longitudinal strain along y and lateral strain along x and z. Sigma 3 will be producing longitudinal strain along z and lateral strain along x and y. So what we can do is we can form a table where we can understand what is the stress due to sigma 1, sigma 2 and sigma 3. So you can write strain due to sigma 1 so along x, along y, along z. Strain due to sigma 2 along x, along y, along z. Strain due to sigma 3 along x, along y and along z. So we have to write down the components of the strain which are acting along its axis and perpendicular to the axis. So we'll start from due to sigma 1. What is the strain along x? Due to sigma 1, the strain along x is nothing but longitudinal strain, which is given by sigma 1 by E. Along y, due to sigma 1, it will be lateral strain, which is given by minus mu into sigma 1 by E. Along z, due to sigma 1, it is again lateral strain given by minus mu into sigma 1 by E. So along x, due to sigma 2, so sigma 2 is acting along y direction. So along y it will be longitudinal strain. Along y it is longitudinal strain. Along x it is lateral strain. So I have to include Poisson's ratio minus mu into sigma 2 by E. Similarly along z also it will be lateral strain. So minus mu into sigma 2 by E. Now strain due to sigma 3. Sigma 3 is acting along z. So along z it will be longitudinal strain sigma 3 by E. Along x it will be lateral strain minus mu into sigma 3 by E. Along y it is also lateral strain minus mu into sigma 3 by E. So we have written 9 components of strain due to 3 stresses, sigma 1, sigma 2 and sigma 3. So along x, sigma 1 longitudinal strain, along y, sigma 2 longitudinal strain, along z, sigma 3 it is longitudinal strain. Now we have to find out what is the total strain which is acting along x, what is the total strain which is acting along y, and what is the total strain which is acting along z. So total strain along x, that is due to sigma 1, sigma 2 and sigma 3. So due to sigma 1, sigma 2, sigma 3, what is the total strain along x? That is nothing but epsilon x. That is, we will add by seeing the components along the columns. So I can write sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E. Next is total strain along y. That is epsilon y is minus mu into sigma 1 by E plus sigma 2 by E minus mu into sigma 3 by E. Last one is total strain along z. Epsilon z equal to minus mu into sigma 1 by E minus mu into sigma 2 by E plus sigma 3 by E. So this equation holds good only when sigma 1, sigma 2 and sigma 3 are tensile or positive. So there will be variation in these expressions when either of these will be compressive. So now once we write the total strain along x, y and z, we can write the expression for volumetric strain, that is equal to sum of strain along that particular direction plus strain in the other two directions. So I can write total strain epsilon V equal to, so that is the volumetric strain epsilon V equal to epsilon x plus epsilon y plus epsilon z. So we'll add all these components of strain. So sigma 1 by E minus mu into sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E plus sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E minus mu into sigma 2 by E plus sigma 3 by E. So we can simplify this equation, and the final result what we will get is the simplifying sigma 1 plus sigma 2 plus sigma 3 by E into 1 minus 2. So this is the expression for volumetric strain in terms of the three stresses and Poisson's ratio and Young's modulus. So if we compare this expression with the first two expressions, the difference was in the first expression either it may be rectangular block or it may be a cylindrical bar, was sigma by E into 1 minus 2. So now we can clearly make out the difference. That is, instead of a single force which was acting here, there are three forces due to which there were three stresses which are acting here. So this plus symbol indicates that all the stresses which are acting was tensile. Suppose if one of the case it will be compressive, you have to substitute positive sign with the negative sign and you have to proceed. So this is nothing but the volumetric strain due to three mutually perpendicular stresses or generalized Hooke's law. Now we solve some problems on this volumetric strain subjected to single load as well as subjected to three mutually perpendicular stresses. Determine the changes in length, width and thickness of a steel bar which is 4 meter long, 30 millimeter wide and 20 millimeter thick and is subjected to an axial pull of 30 kN in the direction of length. Take Young's modulus 2 into 10 raised to 5 Newton per mm square and Poisson's ratio 0.3. Also determine the volumetric strain, change in volume and final volume of the given bar. So they have given a rectangular bar which is four meter long, length is 4000 millimeter, 20 millimeter, that is 30 millimeter wide. So 30 millimeter wide, it is B is equal to 30 millimeter, and 20 millimeter thick, that is depth equal to 20 millimeter. Subjected to a force of 120 30 kilonewton in the direction of length. So it is given that, so we use the same coordinates, along length it is x, along width it is y, along depth it is z. So it is given that axial pull that is along the axis, pull means it is tensile, and they have mentioned where the force is acting. The force is acting along the length. So I can mark force is acting along the length and the value of the force is 30 kilonewton. So this is given in the problem. So they have asked to find out the change in the length, change in the width and change in the depth, that is the changes in the size. So the data what are given are length, width and depth. Force is given 30 kN or 30 into 10 power 3 Newton. Young's modulus is given. So they have given the Young's modulus as 2 into 10 raised to 5 Newton per mm square, and Poisson's ratio mu equal to 0.3. So first we will calculate what is the change in length. So we know that change in length delta is given by FL by A into E. So force is 30 into 10 power 3, length is 4000, area of cross section, that is the area what you have to consider perpendicular to the force what is acting. So perpendicular to the force, the area which is subjected to that force is width into depth, that is a cross section. So cross sectional area is 30 into 20 and Young's modulus is 2 into 10 power 5. So the value of the longitudinal strain what you get is 1 millimeter. So now this is nothing but the change in length, it is delta L. Now you have to find out what is the change in width. So if you observe the problem, along the application of the force there is longitudinal strain. In the other two directions there are lateral strain. So width and depth are related to lateral strain. So we have to use the relation mu equal to lateral strain by longitudinal strain. So for substituting or for calculating the change in width and change in depth, we have to first calculate what is longitudinal strain. So longitudinal strain equal to change in length by original length. So change in length we have calculated it as 1 millimeter. Original length is 4000 millimeter. So the longitudinal strain value comes to be approximately 0.25 into 10 power minus 3. So that is the longitudinal strain. Now from this relation we can write lateral strain equal to mu into longitudinal strain. So mu, that is the Poisson's ratio, it is 0.3. Longitudinal strain we have calculated it as 0.25 into 10 power minus 3. So lateral strain will be getting equal to 0.75 into 10 power minus 4. So in this problem we know that lateral strain equal to either change in width by original width as well as change in depth by original depth. So change in width equal to lateral strain into original width. So lateral strain is 0.75 into 10 to the power of minus 4 into original width is 30 mm. Change in width comes approximately 2.25 into 10 power minus 3 millimeter. Similarly, change in depth, we can calculate the change in depth. So change in depth equal to again lateral strain into original depth, it is 0.75 into 10 to the power of minus 4 into depth is 20 mm. So change in depth will be 1.5 into 10 to the power of minus 3 millimeter. So we have calculated what is the change in length. By using the Poisson's ratio relation we have calculated what is the change in width and we have calculated what is the change in depth. So totally we have calculated what is the change in the size due to the application of this force. So once we have identified what are the changes in the sizes, we can find out what is volumetric strain. So now we calculate volumetric strain. Epsilon V equal to, we have already derived the expression, epsilon V equal to sigma by E into 1 minus 2 nu. Sigma by E is nothing but longitudinal strain. So we can write delta L by L into 1 minus 2 nu. Delta L by L is nothing but longitudinal strain into 1 minus 2 nu. So longitudinal strain we have calculated is equal to 0.25 into 10 to the power of minus 3 into 1 minus 2 into 0.3. So volumetric strain, it is 10 to the power of minus 4. So once we know volumetric strain, we can calculate the change in the volume, that is volumetric strain equal to delta V by V, or change in volume is volumetric strain into original volume. Volumetric strain is 10 to the power of minus 4. Volume is length into width into depth. So delta V, it comes out to be approximately 240 millimeter cube. So once we know the change in volume and original volume, we know that final volume equal to V plus delta V. So that is 4000 into 30 into 20 plus 240 gives you the final volume, which is 2400240 millimeter cube. This is how we can calculate the change in volume as well as the change in the size as well as the different types of strains by using this concept. We'll move on to the second problem. A metallic bar 250 mm into 80 mm into 30 mm is subjected to a force of 20 kN tensile, 30 kN tensile and 15 kN tensile along x, y and z direction respectively. Determine the change in the volume of the block by taking Young's modulus 2 into 10 raised to 5 Newton per mm square and Poisson's ratio as 0.25. They are given again a metallic bar of rectangular cross section. Length is 250 mm. Width is 80 mm and depth is 30 mm. Variation is along x, along y and along z. So they have given forces which are acting on these areas. So 20 kN, 30 kN and 15 kN. That is, along x-axis, the force acting is 20 kN tensile. Along y-axis, the force what is acting is 30 kN tensile. Along z-axis, the force acting is 15 kN tensile. So here there are three forces which are acting in three mutually perpendicular directions. So in order to find out the volumetric strain as well as the change in the volume, we have to first find out what are the stresses induced due to these external forces. So stress along x is sigma 1 or sigma x equal to force which is acting along x divided by cross sectional area. That is, force which is acting along x is 20 into 10 power 3 divided by cross sectional area which is perpendicular to this force That is width into depth. That is 80 into 30. So the value of sigma x is 8.33 Newton per millimeter square, which is tensile. Second, stress along y is sigma 2, that is sigma y. Force acting along y divided by cross sectional area. Force acting along y is 30 into 10 power 3 divided by cross sectional area. So this force is perpendicular to the front face and the back face, that is this face. That is cross sectional area is length into depth, that is 250 into 30. So which comes out to be approximately equal to 4 Newton per millimeter square. So this is again tensile. Last, stress along z axis is sigma 3. So sigma z equal to force which is acting along z axis by area. So force is acting along z is 15 kilonewton divided by cross sectional area, that is length into width. So length is 250 and the width is 80. So this is equal to 0.75 Newton per millimeter square. Again, the nature of the stress is tensile. So now, what is the volumetric strain due to these three stresses? We have the formula epsilon v equal to sigma 1 plus sigma 2 plus sigma 3 by E into 1 minus 2 Newton. So sigma 1 is 8.33, sigma 2 is 4, sigma 3 is 0.75 divided by Young's modulus is given in the problem. It is 2 into 10 power 5 into 1 minus 2 into 0.25. So epsilon v is equal to I can write epsilon v is nothing but delta v by v, or delta v is epsilon v into v. So this is epsilon v into v. It comes out approximately equal to 19.62 millimeter cube, where v is length into width into depth. That is nothing but the volume. So if you multiply this value with the original volume, we will be getting the change in volume, 19.62 millimeter cube. Next problem. A bar 600 mm long is having square section of size 50 mm into 50 mm. If the bar is subjected to an axial load of 120 kN and lateral compression load of 600 kN on faces of sizes 50 mm into 600 mm, find the changes in size and volume. Take Young's modulus equal to 2 into 10 raised to 5 Newton per millimeter square and Poisson's ratio as 0.3. It is given 600 mm long bar. length is 600 millimeter. Width and depth are same, 50 millimeter. Depth is also 50 millimeter. It's subjected to lateral compression load of 600 kN on faces of sizes 50 mm into 600 mm. So 50 mm into 600 mm means that is the top face and the bottom face. The top face and the bottom face. One more is the front face and the back face. That is, along Y there is a force which is acting. The value is 600 kN, and again in the other direction, in the Z direction also it is 600 kN. Both are compression. So one, it will be along Y direction. So we can show along Y direction it is 600 kN. 600 kN. One more is along Z. This is also 600 kN. This is 600 kN. Now along X, so since they have specified that along Y and Z it is lateral, that is compression, along X it should be longitudinal, which is under tension. So along X it is tensile force, that is 120 kN. So along X it is 120 kN, along Y it is 600 kN compression, along Z is it again 600 kN compression. So to find what is the change in size and change in the volume. Okay. So first we will find out what is the stress due to these forces. So stress along X, it is sigma X equal to force which is acting along X, the cross sectional area. So force is 120 into 10 power 3 divided by cross sectional area is nothing but width into depth, 50 into 50, which is approximately equal to 48 Newton per mm square. Inside stress along Y, sigma Y, force along Y axis is 600 into 10 power 3 divided by cross sectional area, it is 600 into 50, which is approximately equal to 20 Newton per millimeter square. It is compressive. Similarly, stress along Z, sigma Z equal to Sz by A. So force along Z axis is also 600 kN, and cross sectional area it is the same, 600 into 50, which is equal to 20 Newton per millimeter square, which is compressive. So we have calculated what are the stresses. Now we will calculate what is the total strain along X, Y and Z direction due to sigma X, sigma Y and sigma Z. So from the generalized Hooke's law, we know total strain along X equal to sigma X by E. So sigma X is tensile minus mu into, instead of sigma Y by E, here I will write minus sigma Y by E. So minus mu into minus sigma Z by E. So inside the bracket, the negative sign indicates that sigma Y and sigma Z are compressive in nature. So this equation gets reduced to sigma X by E plus mu into sigma Y by E plus mu into sigma Z by E. So sigma X is 48 Newton per millimeter square. Young's modulus explain the problem. This 2 into 10 power 5. Continuation of the previous problem. Total strain along the x direction due to sigma x, sigma y, sigma d, sigma z. So sigma x is tensile minus mu into sigma y is compressive. So minus sigma y by e minus mu into sigma z is compressive minus sigma z by e, which is sigma x by e plus mu into sigma y by e plus mu into sigma z by e. Substituting the values, sigma x is 48 Newton per millimeter square divided by x modulus 2 into 10 power 5 plus 0.3, that is the value of the Poisson's ratio, into sigma y is 20 by 2 into 10 power 5 plus 0.3 into 20 by 2 into 10 power 5. So total strain along the x direction is equal to 3 into 10 to the power of minus 4. So this is the total strain along x direction due to sigma x, sigma y and sigma z. So we know that along the x direction there is a length. So strain along x is nothing but change in length by original length, which is equal to 3 into 10 to the power of minus 4. From that, change in length equal to 3 into 10 to the power of minus 4 into original length is 600 mm. So the total change in length equal to 0.13 millimeter. Next, after calculating the total strain along x direction, total strain along y direction equal to lateral strain due to sigma x. So it is minus mu into sigma x is tensile, sigma x by e minus is sigma y by e minus sigma z by e. So minus mu into sigma x by e minus sigma y by e plus mu into sigma z by e. So minus 0.3 into 48 by 2 into 10 power 5 minus 20 by 2 into 10 power 5 plus 0.3 into 20 by 2 into 10 power 5. So total strain along y direction equal to minus 1.42 into 10 to the power of minus 4. So total strain along y direction, so it is nothing but along the width. So change in width by original width, minus 1.42 into 10 to the power of minus 4. Change in width equal to minus 1.42 into 10 to the power of 4 minus 4 into 50. So it will be minus 7.1 into 10 to the power of minus 3 millimeter. Next is total strain along z direction minus mu into sigma x by e minus mu into minus sigma y by e, and along z direction the stress is compressive is minus sigma by e minus mu into sigma x by e plus mu into sigma y by e minus sigma z by minus 0.3 into 48 by 2 into 10 power 5 plus 0.3 into 20 by 2 into 10 power 5 minus 20 by 2 into 10 power 5. So it's along z, total strain along z direction equal to again minus 1.42 into 10 to the power of minus 4. Yes, that's along z. So z is along the direction of the depth. So I can write delta d by d equal to minus 1 1.42 into 10 to the power of minus 4, or delta T equal to minus 1.42 into 10 to the power of minus 4 into 50 comes out to be equal to minus 30.1 into 10 to the power of minus 3 millimeter. So I have calculated what is the total strain along x direction, total strain along y direction, total strain along z direction. That is again change in the size, that is change in length, change in width and change in depth. So now we find out what is the change in volume. So first we have to find out the volumetric strain due to these three mutually perpendicular strains. Volumetric strain equal to algebraic sum of the strains along three mutually perpendicular directions. So we got epsilon x as positive, so it is epsilon minus epsilon y epsilon z. So epsilon x is 3 into 10 to the power of minus 4 minus 1.42 into 10 to the power of minus 4 minus 1.42 into 10 to the power of minus 4. So there is nothing but equal to epsilon x plus minus epsilon y plus minus epsilon z. So epsilon x plus of minus epsilon y is minus epsilon y, plus of minus epsilon z is minus epsilon z. So epsilon v equal to 0.16 into 10 to the power of minus 4. Epsilon v is nothing but change in volume by original volume, 0.16 into 10 to the power of minus 4, or change in volume equal to 0.16 into 10 to the power of minus 4 into volume of the block, that is 600 into 50 into 50. So change in volume comes to be approximately 24 millimeter cube. So this is nothing but the change in volume due to the three mutually perpendicular strains.